Hello, I am going to be showing off my custom feature for my game engine, which I am calling the ExSprite Engine. The feature that I have added over the past 2 weeks is custom shader support. It also adds several other features that help complement this, such as being able to create compute buffers, being able to create custom meshes, as well as also being able to run compute shaders on top of just vertex and fragment shaders for normal graphics rendering. Um, so from last week, the biggest improvement, or the most notable improvement that was made that I wanted to make, is that shaders are no longer manually compiled. So before, what I would have to do is I would run, every time I made a change, I would go down to my terminal and run a compile script, and I no longer need to do that. Instead, let me open up the file. The shader programs are written directly in HLSL, and the program compiles it from HLSL into the SPV files that the program previously wanted. So that was done using the DirectX compiler. The DirectX compiler can compile from HLSL into several other shader languages, such as DXIL, which would be used if I wanted to add support for Direct 3D12, but I'm only adding support for Vulkan right now, so all I need is the SpearV files. The SpearV files, as before, are given into the Spear of Cross library, which is used to get a lot of reflection information about the different data layouts, the different buffers, the different textures that each shader uses, so that my program can dynamically assign those values at runtime. A lot of new API is introduced into Lua. So for example, the first is materials. So the materials are instantiated by using the name of the shader that you want to create it from. Previously, it required a separate vertex and a fragment shader separately. Now, the program assumes that both the vertex and fragment shader stage are written into the same file. This just helps ensure that different data layouts are the same between the two, so that the program only needs to manage one copy of that data, which helps simplify things and makes it a little bit more efficient. It does remove a little bit of flexibility, but in general, that's not really something. It's not the sort of flexibility that you would really use in any actual application. The rest of the material API is pretty much the same. You can modify the material that gets used in the old existing image draw calls. You can set different values for the material to use within the shader. The only new feature is the set buffer, which is the compute buffers I'll get into a little bit later. Other than that, the only thing... Okay, yeah, so you can create custom meshes using the vertex class. Meshes can be modified a lot of different ways, by adding a vertex, setting vertices, adding triangles, adding quads. Has a couple of getter functions, and then after changes are made, you call upload to tell it to upload that data onto the GPU version of the mesh. So as before, there's the existing two draw commands that are basically the equivalent to the old draw and draw EX, only with an additional material, which basically serves as like an override of what material this draw call should use. Render quad is the same as before, just manually rendering a quad using a specific material. Render mesh is also the same. Instead of a quad, you're just rendering a mesh that was previously created by your program. And then the new one here is render mesh instance. This again, I'll get into a little bit later when I talk about compute buffers. But as for what you can do with this, as I showed before, effects that you could previously create using very tedious methods are now much easier. So in the earlier version of the engine, something like this would have to be done using a ton of individual pixel draws, but now it can be done using a single draw call and is able to render very, very complex visuals a lot more efficiently than you would otherwise be able to. One great advantage of manually compiling shaders is that, or compiling shaders at runtime, is that you can also recompile shaders at runtime. So, for example, let's see, I have to go in and open where this shader file is to show this off. Let's see. Shaders, here we go. So if I were to bring this out here just so I can see them both at once, change how the colors are rendered, it will immediately apply at runtime, so it'll recompile the shader and affect the visuals without needing to rerun the program. So that's really the biggest benefit of not needing to manually recompile. Next, the biggest improvement, the biggest addition I've made since last week is the addition of compute shaders on top of just doing, sorry, I'll talk about compute buffers next actually. So compute buffers is another thing that's been added. You can create a compute buffer by defining the size and the type. Currently, the supported types are integer, float, float2, float3, and float4. The size is basically just an array of how big it is, what size it represents on the GPU. You can use set data to pass data into the buffer. You can use get data to retrieve data from the buffer, and then release when you're finished using the buffer. This combines well with the render mesh instance and the, let's see, what was it? Material.set buffer, where if you pass in a buffer of information, you can render multiple objects using one singular draw call, using data that was pre-computed and uploaded to the GPU. So to give an example of this, let's see if I can remember what I called this test case. I think it was this. Yeah, so it's going to take a few seconds. It's computing all the data, and then once it finishes uploading, it renders it all. So it's rendering a million different quads using one singular draw call. All of the information about each individual quad, such as the position, rotation, scale, and color, are all passed into individual buffers, and each quad call, or each quad just accesses its specific index within that buffer and allows for all of this data to be computed and rendered each time with no work being done by the CPU after that first initial upload. So you can see, let's see. Okay, I removed the outputs, but before you could see when they were being uploaded. Yeah. Now, one thing that makes compute buffers a lot more useful. So you saw at the start of this test case, it takes a couple seconds to boot up, which oftentimes is not very ideal. It would be much better if that could be very quickly and instantly populated, and that's where compute shaders come in. So compute shaders are pretty similar to regular shaders, but instead of rendering on a render texture, you can use them to, instead of using them to draw to specific points on a texture, you can use them to read and write to different types of buffers. They can also be used to access textures, but they're most often used with buffers. So you just dispatch it, tell it how many thread groups you want it to use on the GPU, and then you run that. So let me find, what was the test case called for this? Compute shader. Okay. So when I run this one boots up instantly, unlike the last one. Oh, actually, I forgot to, I made some changes with how the rendering works, and I didn't end up fixing this one. So I can't show this one right now, but what this would have seen is a result very similar to the previous test case where it has a million objects being drawn, but instead of computing on the CPU and uploading to the GPU, it just computes on the GPU directly using a compute shader, and that causes the loading stage to be practically instant, as opposed to the several seconds of loading that was done without compute shaders. Yeah, but I forgot to update that test case. So once you put all that together, you can create a lot of really cool effects. And one example I have to show is a old Unity game of mine that I ported over. Let's see. Oh, spelled it. So this test case doesn't use compute shaders, but it uses all of the buffers and custom shaders as before. So you can see a lot of really cool effects, and especially when you have multiple objects interacting, you can make really cool effects that would otherwise be impossible using just traditional image and sprite rendering. This is done by passing all of the different objects that are to be drawn as all of the parameters into different compute buffers, and then computing what each individual pixel should be based on its proximity to each of those different objects. So it looks especially cool once you get multiple objects interacting with each other. And yeah, this is just something that you would not be able to do without these more advanced rendering techniques. Yeah, so another thing I didn't talk about earlier is actually detecting how shaders are changed. Let's see. Yeah, so it uses, originally I looked at this file called, or this program called File Watcher. Unfortunately, I couldn't get this to compile with my engine for some reason, so I ended up creating a similar version of it on my own. Let's see, File Watcher, and basically what it does is it looks at the shader folder, uses a recursive directory iterator, saves all of the different times that those paths were last changed, and then it iterates through them, and every time it finds a new one to change, it queues it to be recompiled. There was a couple things I wanted to do that I didn't get around to doing. For example, the particle systems would be a perfect application of, building in the compute shaders and rendering to make that a lot more efficient. And that's something that I absolutely could work on, but I didn't get around to it in these 2 weeks. Let's see, was there any other test cases I wanted to show? Just take a look. Oh yes, so I can show the trail render. I showed this one in the last week's video, but this is basically a slightly more advanced application of the custom meshes that have been seen. I think all the ones I've shown up until now just use basic quads, but this one recomputes a new mesh every single frame based on the images that have been saved, or based on the positions that have been saved with the mouse position, and uploads that mesh to the GPU to be rendered every frame. And you can create really cool effects like this. Again, this is something that without more complex rendering techniques would be nearly impossible to do using just regular image drawing calls. But yeah, overall, I really enjoyed working on this project. I feel like I understand the, GPU API is a whole lot more than I did before, and I also really enjoyed working on it. I'm really proud of how the engine and the custom feature turned out. There's still a few things I think I'm probably going to work on even after the course, but yeah, I'm really happy with where it's at. So yeah, thank you for listening, and yeah.